Okay, so let's go ahead and get started. So far in this class, we've developed some ways of studying the computation of scattering amplitudes and correlation functions in quantum field theory perturbatively, and we developed a perturbative approach based on the Schwinger-Dyson's equation and based on sort of very general considerations about the behavior of correlation functions in quantum field theory. And today what I'd like to start doing is developing an alternative approach based on the path integral formulation of quantum mechanics. And as many of you probably already know, the path integral formulation of quantum mechanics is useful really not so much as a calculational tool, at least in standard quantum mechanics, but more as a way of organizing your thinking and of clearly seeing certain effects that I think are easy to see in the path integral formulation that are more obscure in other ways of thinking about quantum mechanics. And I think in quantum field theory, this is true to an even greater extent, which is that there are certain things that we need to understand about quantum field theory that are, if not impossible to understand, at least very difficult to understand without using the path integral formulation. And indeed, it's primarily because of quantum field theory that the path integral formulation of quantum mechanics is taken seriously. So you could, if you were only interested in non-relativistic quantum mechanics of particles, of moving in potentials or something like that, then you could certainly go your whole life without ever thinking about path integrals, and you would be just fine. It was really only in the 1970s when people were trying to understand the behavior of gauge theories in the Standard Model that it really became apparent that there were certain things that you could only understand if you took a path integral approach. Okay. So for now, what I'm going to do is just give you, for a lot of this class, really a brief reminder of the path integral formulation of quantum mechanics, which will then generalize very easily to a path integral formulation of quantum field theory. And then we'll go back and we'll rederive some of these Feynman rules for the calculation of correlation functions, both in position and momentum space, that we encountered over the last few classes. Okay. So I'm just going to begin with a brief review of path integrals in quantum mechanics. If what I'm saying is boring to everyone, or if you've seen this all before, please feel free to encourage me to speed up, and I can skip over some of the basics. But I thought just so that we're all on the same page, I might just start by reminding you of the role of path integrals in quantum mechanics. Okay. So let's just start by thinking about a quantum mechanical system with some number of degrees of freedom. We could call them, say, Qi, where I is an index that runs from 1 up to n. Or we could also consider a quantum field theory which has an infinite number of degrees of freedom, 1 per point in space-time. And so then we typically call our degree of freedom something like phi, and we label it by a position, a spatial position x. But for now, I'll just restrict my attention to the finite dimensional case. And let's imagine that we want to compute the transition amplitude for the system to start with some initial, at some initial configuration Q initial, and transition to some final configuration Q final at some later time. Okay. So for now, I'm just going to imagine I'm thinking about 1 degree of freedom that I'll call Q. You can go back in and add the other indices later on to consider many degrees of freedom. You could add an infinite number of them to consider an infinite number of degrees of freedom, as we do in quantum field theory. But for now, let's just focus on a single degree of freedom. Okay. So the basic, so of course, usually the way that we would compute this is we would solve Schrodinger's equation. You would start, say, with an initial state where your particle is at, where Q has a particular value at time t initial. You would evolve with a Hamiltonian, and then you would compute the wave function at some later time. Okay. What I would like to do, however, is try and develop an alternate way of thinking about this which is really based on the superposition principle of quantum mechanics. Okay. So in particular, what I would like to do is use the fact that we can always insert a complete basis of states at any intermediate time. So we can always insert a complete basis of states at some time. Let's call it, say, t. That's sometime between t initial and t final. Okay. So that means that if you want to compute the amplitude for this particle to transition between, say, position q initial and some other position q final, then you could just, let's just call q, well, maybe to make my notation a little bit simpler, what I'm going to do is instead of calling them q initial and q final, I'll call them q1 and qn, where n is some integer. Okay. So here, t initial is t1, t final is tn, and so forth. And then what I'll do is I'll introduce some intermediate time t2, which is between t1 and tn. Okay. And then I'll insert a complete basis of states at time t2 and sum over that basis. Okay. So again, as usual in physics, all I'm doing here is rewriting 1 in a very complicated way. Okay. So this is a complete basis of states. So I haven't actually done anything here. Okay. So now I'm not going to do anything n more times. Okay. So what I'm going to do is now imagine that I insert n bases of states at some times t2 up to tn minus 1. Okay. So that means I need to integrate dq2 all the way up to dqn minus 1 of the amplitude for a particle to go, say, from position q1 at time t1 to position q2 at times t2, all the way up to the amplitude for the particle to go from qn at tn minus 1 to qn at time tn. Okay. So all I'm doing here is saying that the amplitude for a particle to go from position q1 at time t1 to qn at time tn is the sum of the amplitude for the particle to go from q1 at t1 to q2 at t2, then to go from q2 to q3, q3 to q4, and so on and so forth. For some choices of intermediate times, t2, t3, and so forth, all the way up to tn. Okay. So if you wanted to draw a little picture to go along with this, we would imagine that you start, let's say that q is the position of your particle in, say, the x direction. Then you would start with a position here. Then q2 would be some intermediate position right there, which we would integrate over. So here time is going, increasing to the right here. So then you would have q3, and so on and so forth, until finally you get all the way up to qn. Okay? And so you can think of each of the individual terms in this integrand as the amplitude for the particle to move from one of these positions to the next as time increases. Okay? And what we'd like to imagine doing is taking the limit then, where n goes to infinity, and the differences between these times, say ti minus 1, which I'll call delta t, goes to 0. So then, if you do that, then you can see that in this expression, the amplitude for the particle to go from q1 to qn then becomes a sum over all of the possible ways that the particle could go through any possible intermediate position. Okay. So as n goes to infinity, this becomes a sum over paths. Or more generally, if you're not talking about the position of a particle through space, but rather some more general quantum mechanical system, a sum over all possible classical configurations of the system, subject only to the boundary condition that q at time t initial is equal to q initial, and q at time t final is equal to q final. Okay. So what this means is that schematically, we expect there to be some sort of expression really just based on the superposition principle of quantum mechanics, which says that the amplitude for a particle to move from one position at early time to another position at late time should be some sort of sum over all possible configurations, subject only to the boundary condition that, q initial at q at t initial is q initial, and q at t final is q final. Okay. I guess I called these 1 and n, not initial and final here. Okay. So the question then, well, there are really two questions. So the first question is, can we make sense of this expression where we have a sum over all possible paths? In classical mechanics, in standard calculus, we're used to integrating over a finite number of degrees of freedom. Here, you're integrating not over a finite dimensional space, but rather an infinite dimensional space, the space of all possible functions q of t. So it's not even clear exactly how to define such an object. For example, the standard definitions of integrals that you would look up in your calculus books wouldn't apply here. We don't even know how to, for example, define a measure on the space of functions. But even if we could determine exactly how to define such a path integral, we also need to determine what exactly this something is here. Okay. So before I go on and determine exactly what this something is for you by doing a short little calculation, what I'd like to do is actually suggest to you a way that you could guess the answer without even having to do any work whatsoever. Okay? And the way that we could guess the answer would be based on thinking about the classical limit. Okay? And in particular, what I want to do is think about the classical limit, remembering a particular approximation scheme that we typically use when we think about classical physics. Okay. So, in particular, we know that as you take a classical limit, so that as you take h bar to 0, this amplitude should depend only on the classical path through configuration space that the particle takes, which solves the equation of motion of the theory, which is the Euler-Lagrange equation, namely the variational derivative or the functional derivative of the action with respect to q is equal to 0. Okay. So that's dl by dq minus d by dt. dl by dq dot has to be equal to 0. Okay. So we know whatever this something is, it has to have the property that as you take the limit where h bar goes to 0, the only contribution to this integral should come from the particular path that solves this equation. Okay. So, in fact, now let me remind you, or if not remind you, teach you, an approximation method for performing simple finite dimensional integrals, which will immediately make it clear what sort of expression we should have for the something in order to have the property that in the classical limit you localize onto the path which solves the classical equations of motion. Okay? And that is known as the method of saddle points, otherwise known as the stationary phase method. Have you guys seen this in your classes on integrals or calculus or something or another? Some of you have, some of you have not. Okay. Well, don't worry. You'll get some practice with the method of saddle points on your problem set for next week. Okay. So let's just consider the following integral. So let's consider the following one-dimensional integral. Okay. So let's just imagine that q is a single variable. Okay, it's not a function, it's just a single variable. And let's do an integral that looks like e to the lambda f of q. Okay. Where lambda is some parameter and f is some function. Okay. So f will look something, say, like that. Okay. And I'll take it to vanish as q goes to plus or minus infinity, so that this integral is nice and convergent. Okay. Or rather, I guess I would need it to go to minus infinity, okay, as q goes to infinity. Okay. And I'd like to understand this integral in the limit where lambda becomes very large. Okay. And in particular, if you just stare at that integral, then you can easily convince yourself that as lambda goes to infinity, z is going to be dominated by the local maxima of the function f regarded as a function of q. Okay. So, in particular, z should be given by something like the sum over all q which have the property that f prime of q vanishes. Okay. So you should sum over all of these points. So there's a point right there. That's the global maximum, q naught. So there's another one right there. There's another one, and so on and so forth. And I think if you just stare at this integral, you can convince yourself that when lambda goes to infinity, the leading contribution to this integral will come only from these local maxima. Okay. So here I've written down only the leading contribution. One can also compute subleading contributions. And by one, as usual, I mean you on your next problem set. So because f prime is equal to 0 at the saddle point, the first leading contribution should involve f double prime. This is what it looks like, plus so on and so forth. Okay. So we can see that in this case, when you're doing a finite dimensional integral, the way that you have an integral that localizes on certain values, say where the derivative of f with respect to q is equal to 0, is you have a function that is your integral, your integrand just depends on f. Okay. Now, in the case of the path integral of quantum mechanics, we want our integral to localize on those configurations where the functional derivative of s with respect to q is equal to 0. So that naturally means that we expect this transition probability to be a sum over all paths of something which is a function of this classical action. So the classical action regarded as a function of the path that you take through configuration space. Now, we want this to localize on classical paths when h bar goes to 0. The action has dimensions of h bar, that is to say dimensions of energy times time. So really, we need this to be some function of 1 over h bar times the action. Okay. So now let's go ahead and see if we can figure out precisely what function it should be. Okay. So let's just go ahead and compute this guy directly. Any questions before I continue?
This sum, you are considering also the mean?
Yes. So now, of course, well, okay. I mean, one has to be a little careful. So strictly speaking, when I talk about this expression, I only want to talk about the maxima, because at the minima, f double prime, well, you can see that funny things will happen. So f double prime will be negative for the minima rather than positive. And so you'll get an imaginary contribution to this coming from one of the local minima. So really, we should only be talking about maxima. However, in the case of quantum field theories, things can get a little more subtle. There are cases where we'll be doing path integrals of this sort, and the contributions that have i's here can in some cases be physical. Okay. So in general, there's actually a rather complicated procedure known as the method of stationary phase for determining exactly which saddle points or local minima, local extrema of the function f will contribute to the integral. It's a rather subtle mathematical subject that I don't want to get into too much. So for right now, let's just focus on the maxima, okay? But we'll keep in mind, I mean, I don't think it'll be within the scope of this class, even next semester. But you may want to keep in mind that there are some cases in quantum field theory where you will want to consider other extrema, and they will have a nice physical interpretation. Okay. Good. Yeah, so for example, in quantum, well, okay, let's not talk about it. Even in quantum mechanics, there are cases where that can have a nice physical interpretation. But let's not go into that. Okay. So let's go ahead and compute this guy. Okay. So what I want to go ahead and do is sort of complete the process that I started earlier. So I want to think about this as, first I want to imagine discretizing the time interval between t1 and tn, and let q2 up to qn minus 1 denote the position of the particle at this intermediate time. And then we have this product of transition amplitudes, where you first have to calculate the amplitude for a particle to move from Q1 up to Q2, and then Q2 up to Q3, and so on and so forth. And you compute that transition amplitude just by inserting a factor of the Hamiltonian, of e to the I Hamiltonian times the time interval delta t. Okay. And just for simplicity, I'm going to consider the relatively simple case where the Hamiltonian is just that of a free particle moving in some potential. Okay? It's not too complicated to generalize this, but this will just keep some of my formulas a little simpler. Okay. So then, in order to compute this transition amplitude, I'd like to use the following trick. What I'd like to do is use the fact that e to the IH, I guess minus IH delta t, what is that? Well, that's e to the minus I times 1/2 p squared plus v delta t. What I'd like to do is I'd like to go ahead and rewrite this as a sum of two terms, one of which is the kinetic term, and the other of which is the potential term. Okay. Now, of course, that looks all nice and kosher, except, of course, this formula is completely wrong. The reason why this formula is completely wrong is that P and Q don't commute, so P and V don't commute, and so you can't just write a formula e to the a plus b is equal to e to the a times e to the b when a and b don't commute. Okay. Fortunately, we can understand what the corrections to this formula look like. Okay. The first correction involves the commutator of a and b, and if a here is p squared delta t and b is v times delta t, then this commutator will be of order delta t squared. Okay. And indeed, all of the other higher terms in this formula will be of order delta t squared. And we'll be considering the limit where delta t is very small, so that I'm just going to neglect all of those terms that are higher order in delta t. Okay. And indeed, as maybe you've seen the Campbell-Baker-Hausdorff formula, which is the name for this formula right here, before, and all of the higher order terms in the Campbell-Baker-Hausdorff formula, indicated by this dot, 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 they're all higher and higher commutators of a's and b's. Okay. The next term is like the commutator of a of the commutator with a and b, plus various other triple commutators and so on and so forth. Okay. Okay, so that's trick number one. Okay. Trick number two is I'm also, in addition to inserting this this large n number of intermediate position eigenstates, I'm going to also insert an infinite number of momentum eigenstates. Okay. So what I'm going to do is at each time t2 up to tn minus 1, I'm going to insert a momentum eigenstate that I'll call, labeled by some momentum p2 up to pn minus 1. And then the term here in the sum, so I'll have qn, so what do I have? I have an e to the, using this formula right here, minus I p squared delta t. So, and what I'll do is I'll insert a complete momentum basis here. And then you have to take the product over all of the various terms, all the way down to q2 e to the minus I p squared delta t p1 e to the minus I delta v, sorry, there's no delta here, v delta t q1. Okay, so all I've done here is I've just used the fact that when delta t is small, I can approximately factorize those terms in the Hamiltonian. And then I can insert a complete basis of momentum states right here, which allows me to just use the fact that here I have a p squared acting on a momentum eigenstate, and here I have a v, which is a function of q, acting on a position eigenstate. So I can just compute exactly what these matrix elements are. Okay, so I get an integral dq2 up to dqn minus 1, along with an integral dp2 to dpn minus 1. Actually, I suppose it's an integral dp1, right, up to dpn minus 1, isn't it? Because I have to insert n minus 1 momentum states, not n minus 2 here. Okay. And what do I get? Well, I get e to the, so from this term right here, I get an e to the minus I pn minus 1 squared delta t. And then from this term here, I get a minus I. So let me just collect all of those terms. Oh, there's an over 2 here. So minus I times p n minus 1 squared over 2 plus v of q n minus 1 all times delta t. And then I have the wave functions, so the overlap between qn and pn minus 1, and the overlap between pn minus 1 and qn minus 1 here. So I get an e to the I pn minus 1 times qn minus qn minus 1. Okay. Times all of the various terms all the way down to n equals 1. Okay. So if I want to, maybe I should write a product over all. Yeah, okay. Let me not use that notation. So there's one important thing to note here, which is that essentially what I did is I first took this Hamiltonian, which was the exponential. I took e to the Hamiltonian, and I used Campbell-Baker-Hausdorff to split it into 2 parts. Then I inserted a momentum space basis. I evaluated it in this momentum space basis, where now this is just a function. This is not an operator. So e to the a times e to the b, if a and b are functions, is just e to the a plus b. Okay. So there's no commutators there to worry about. And so I then have this product of the n terms, and so I get an integral dq2 all the way up to dqn minus 1, dp1 all the way up to dpn minus 1. And I have the product of a bunch of exponentials, which is the same as the exponential of a sum, where now I sum over all I of, what do you get? Well, you have minus I times the Hamiltonian as a function of pi and qi times delta t minus pi times qi plus 1 minus qi. And I'd like to pull out an overall delta t, so I'll just divide that by delta t. And now what I'd like to do is take the limit where delta t is going to 0. So this is just qi plus 1 minus qi over delta t. What is that? That, by the definition of the derivative, is just q dot. So what do we have here? We have an integral in the limit where delta t goes to 0 over all possible positions that the particle could take. So that's an integral dq, as well as an integral over all possible momenta that the particle could take. So I'll call that dp of the exponential of I times this sum over I in the limit where delta t goes to 0. But if you think about it, the sum over I of some function evaluated at position qi, momentum pi, in the limit where n goes to infinity will just become a continuous integral dt from t1 up to tn of p q dot minus h as a function of p and q. Okay. Are there any questions on this so far? I mean, I should emphasize that I haven't really defined precisely what these symbols dp and dq are. Okay. That's intentional because they have no precise definition. This is really, you should, if you want to try, you should think about the definition of these symbols precisely as this discretization that I'm performing right here. Okay? I mean, there's really no other way, I think, that we know how to define a functional integral precisely. There was a question in the back? Yes.
If you have started in the beginning with momentum, I can say, for example, at some initial time, you have
Absolutely. Yeah.
and then we do the same trick with the Hamiltonian, the exponential, and after that we insert it to give the basis but position.
Yes. So.
Then we will end up into the same.
Good. Okay. This point. Okay. Right. So that's an excellent point. Okay. So what we've done is express this transition amplitude as a path integral not over all configurations, but over all of phase space. So this is a path integral over all trajectories, not just through configuration space, but through phase space. Okay. So at this point, the expression that I've given here looks completely democratic, looks like it treats P and Q completely democratically. The only place where it doesn't treat P and Q completely democratically is through the boundary conditions. Because the boundary conditions, remember, are that Q at T1 is equal to Q1, and Q at Tn is equal to Qn, but the momenta are unconstrained. Now, if we had instead tried to compute the initial, the transition amplitude between momentum eigenstates, instead of position eigenstates, we get the exact same expression except that the boundary conditions on the path integral would be different. Okay. Okay. So what we've discovered here is not the path integral formulation where we integrate over configuration space, but a path integral where we integrate over phase space. So sorry, okay. So phase space is the set of all possible Q's and P's. Okay. So phase space is the QP plane. Okay. And classical trajectories are paths through phase space. Okay. Usually closed paths through phase space if you have periodic motion, for example. Okay. Whereas configuration space is the set of all possible Q's. Okay. So when we integrate over all paths through phase space, we're integrating over all functions Q of t and P of t. Whereas when we integrate over all configurations, we're integrating just over all Q of t. Okay. So the question then is, can we reinterpret this expression where we integrate over all paths through phase space as an integral over all configurations? And this is the case, this is the case, this is the reason, so this is the point where our assumption about the form of the Hamiltonian will become important. Okay. In particular, since our Hamiltonian, H, is quadratic in P, the P integrals are just Gaussian integrals. So we can just do them and rewrite this just as an integral over all of the Q's, not just all of the P's. Okay. In particular, what does one of the P integrals look like? Okay. So let's just stare at this formula here. We get an integral of a P squared term here and a P term here. So one of these P integrals would look like an integral dpi times e to the I. So I have a minus 1/2 pi squared. That was coming from the Hamiltonian, the minus Hamiltonian. And then we had minus, sorry, I guess it was a plus pi times qi dot. And that is a Gaussian integral that we know how to do. You just do it by completing the squares. and you get some number that we aren't going to particularly care about, times e to the minus I, sorry, e to the plus I qi dot squared over 2. If you don't remember all of these Gaussian integrals, don't worry. You'll have a chance to review them on your next problem set. And this number I'm not going to worry about very much, because I don't really know what this symbol dq means anyway. So any extra numbers that appear, I'm going to define to be part of dq. So that means that I can think about this. So, well, in particular, what does that leave us with the integral? Well, we have an integral of e to the I qi dot squared, and then we have the potential term right here, and we have a name for q dot squared plus the potential. That's the Lagrangian. So that implies that this transition amplitude is now just an integral over all paths through configuration space rather than phase space of the integral not of pq dot minus h as we wrote up there, but just of the Lagrangian, now regarded as a function of q and q dot. Indeed, hopefully you remember the definition of the Hamiltonian was p q dot minus L. So that means that p q dot minus the Hamiltonian, it's just another way of writing the Lagrangian. Okay. Oh, and there was a factor of I out front. Okay, that's this factor of I. Or, restoring our factor of h bar, this transition amplitude is the integral over all paths of e to the I action of a path through configuration space divided by h bar. Good. Okay. So let me just make one or two comments about this. So as I emphasized, path integral expressions like this are generally speaking not rigorously mathematically well defined. Okay. We understand how to do them when we have Gaussian integrals. We also understand how to do them when we have a perturbation series around a Gaussian integral. Okay. That's the theory of Feynman diagrams that we will be developing. But in general, we don't know what an expression like this means in a more general setting, where we don't have any perturbative expansion. Okay. There are some cases, such as in what's known as lattice quantum field theory, where people try and define these path integrals exactly without using any perturbative expansion. And in that case, you can then go ahead and try and compute them numerically, where you literally perform some numerical integral where you discretize the space of all possible positions, as we have done here. And in that case, that is something that we do appear to, we can study numerically. But there are all sorts of subtleties having to do with renormalization, which is something that we'll be studying a lot in the second semester of this course. And indeed, even in those cases, it's only in certain circumstances that we really know how to rigorously define these. Okay. Nevertheless, there are certain things that are really made manifest only when we consider the path integral formulation of quantum mechanics. Okay. So for example, there's some things like quantum mechanical interference, okay, that are almost obvious if you look in the path integral formulation. You think about the double slit experiment, and you think about a particle going through both slits at once, okay, in the double slit experiment, the Stern-Gerlach experiment. This is something that is kind of a little mysterious from the Hamiltonian point of view, but from the path integral point of view is completely obvious, almost. It's obvious, clearly the transition amplitude for a particle to go from one side of the slit, one side of, some double slit experiment to the other will involve the particle contributions from both possible paths that the particle can take through these two slits. Okay. Similarly, there are certain things involving theories with symmetries that are made much more clear when you think about the path integral formulation. The way that gauge symmetries act in quantum field theory is much clearer in the path integral formulation. And indeed, in the quantum theory of gauge symmetries, you really can't get the correct Feynman rules using the Schwinger-Dyson equations that we wrote down the other day. You really need to think about this path integral formulation. Good. Any questions before I continue? Indeed, we're going to see in the next few minutes that many of the quantities that sort of might have seemed a little ad hoc in our previous discussion of quantum field theory will become completely natural when we think about this path integral point of view. Okay. So, of course, in quantum mechanics, much less to say quantum field theory, we're not just interested in studying transition amplitudes. We're also interested in computing expectation values. Okay. So, for example, let's say that instead of computing just a transition amplitude, I want to compute the expectation value, or the matrix element, of the operator Q between these two states. So here T is some intermediate time between T1 and Tn. So how could I go about computing this? Well, I could just introduce an intermediate set of states at time t at this intermediate time. So I'll call the eigenvalue of one of those states Q, and we'll just integrate dq of the amplitude to go from, say, Q at time t to Qn at time Tn, along with the amplitude to go from our initial time to this intermediate time t. So T1, Q1, and T1. Okay, and now, of course, Q of t acting on Q is just gives you Q. This is one of those cases where you regret suddenly calling every variable Q. Okay, this state here is an eigenstate of capital Q, so we can just pull this out, and you get the function Q at t of Qn Tn Qt. Okay. So that's this guy here. Okay, so what's going on here? We see that all that happens when you want to compute an expectation value is you get an integral, you get the amplitude to go from Q1 at time T1 up to Q at T, and then Q of T up to Qn at time Tn, and then you integrate dq. Okay, so that's just the same path integral that we've been studying. The only difference being that you now have this extra insertion of Q of T. So what is this? This is otherwise known as the integral over all paths of the same quantity that we've been studying, so e to the is over h bar, with an insertion of little q of t. Okay. So to summarize, and this is a very important point here, if you want to compute the matrix element of an observable using the path integral approach, you just take the function Q of t and you insert it in the path integral. Okay. Now, there's a couple of important points that we should make here, which is that, so the first important point is that this path integral expression is an integral over all classical fields. It's an integral over all classical configurations. There are no operators appearing anywhere. Whereas capital Q here is an operator. And so if you want to compute the matrix element of the operator Q, you just take the classical variable corresponding to Q, and you insert it in the path integral. I mean, it's sort of magic. Okay? The matrix element of a quantum mechanical operator in the path integral formulation just becomes the insertion of the classical variable corresponding to that operator into the path integral. Is that clear, more or less? Good. Okay. Now here comes the magic. Okay. So what happens if you want to compute something more complicated? What happens if you want to compute, say, the matrix element not of 1 power of Q, but 2 powers of Q? Okay. Well, naturally, you would expect this, based on our previous discussion, to be something like the path integral, where you now insert both a Q of t and a Q of t prime. Okay. But if you think about this, there's something very confusing about this. Okay. Because here we have two quantum mechanical operators on the left-hand side, which don't commute. But here we just have two classical variables. Those are functions, Q of t and Q of t prime. They commute with one another. So this expression that I've written down can't be true, as I've written it. Because, for example, what would happen if you wanted to reverse the order of the capital Q of t and capital Q of t prime on the left-hand side? Well, that is clearly not going to be equal to the same thing that we've written on the right-hand side, yet the classical variables Q of t and Q of t prime commute. Okay, so what's the resolution of this? Well, the resolution is, let's just ask what would happen if you started trying to compute explicitly e to the is of q over h bar times q of t prime for some values of t and t prime that are between t1 and tn. Well, if you wanted to compute this, you would have to divide into two different cases. First, you would have to consider the case where t is bigger than t prime. Okay. So if t is bigger than t prime, then first you just redo the argument that we did up here, where you insert a complete basis of states that evolves first from t1 to t, and then, if t is bigger than t prime, okay, then you first evolve from t1 to t prime, then t prime to t, and then t to tn. Okay. So if t is bigger than t prime, you'll get the expectation value of q of t prime in the state q1, the matrix element of qt prime. On the other hand, if t happens before t prime, then you'll need to do things in the opposite order. And you'll get q of t prime on the left and q of t on the right. Okay. Now, we had a name for correlation functions where you have to order the operator so that the later operator always happens on the left. We call those time-ordered expectation values. Okay. So you see that in the path integral formulation, the correlation functions that you compute are actually time-ordered correlation functions. And indeed, as we saw in our discussion of scattering amplitudes in quantum field theory, this is exactly what we need. We only need the time-ordered correlation functions. Any questions on that? So the path integral naturally computes time-ordered expectation values simply by inserting them as classical variables in the path integral. Any questions on that before I continue? Yes. Okay. You mean, okay. So let's just look at this expression here. Let's look at the right-hand side of that equation. Okay. What is this? This is a sum over all functions q of t. Okay. By classical variable, I mean a function. Okay. So for example, on the left-hand side here, I have a bra and a ket, which are elements of a Hilbert space and a dual Hilbert space, and I have an operator which acts on that Hilbert space. On the right-hand side, I have an expression that involves no Hilbert space. It involves no operators. There's no bras and kets appearing in that expression. Instead, what I have is an integral over all possible functions q of t. And so when I say that q of t here is a classical variable, I mean it's literally a function. Okay? I mean, it's kind of remarkable because you spent all of your lives as quantum mechanics being indoctrinated that quantum mechanics is nothing like classical physics and there's no classical variables and blah, blah, blah. But in the path integral formulation of quantum mechanics, you really can, in a sense, think about things in this more classical language. Okay? That's really why the path integral approach is so useful. It makes the correspondence between classical and quantum physics much more apparent. So when I say it's a classical variable, I mean it's a function. You know, q of t is a number. Okay, it's the function q evaluated at time t. And as you know, and the point here is that the function q evaluated at time t is this times the function q evaluated at time t prime is equal to the function q evaluated at time t prime times the function q evaluated at t. Okay, so these guys commute, where these guys don't commute. Yes?
So if you still up halfway, maybe I'm missing something, but I wonder how we know that q and t that you inserted in there
Yes?
are eigenstates of the q of t operator. Like
Okay.
getting from the first line to the
So
line.
what I'm doing is I'm trying to compute the matrix element of the operator x at time t. Okay. So I'm working in, I guess I could say that I'm working in the Heisenberg picture, where q has some explicit dependence on time. Of course, when you write down a matrix element like this, the Heisenberg and Schrödinger pictures are the same. Okay, it's just a matter of where you put the e to the IHTs. Okay, but yeah. So for example, if I have a some path through configuration space, then, or some quantum mechanical process where a particle moves from position q1 at some early time to position qn at some later time, then you want to ask, what is the expectation value of the position of the particle at some intermediate time?
And then let's say we go from the first line there to the second line,
Yes.
and you pull out the q of t from classical function.
Yes. I mean, I'm inserting a complete basis of states here at the intermediate time t. That's just where I choose to insert them.
That are eigenstates.
That are eigenstates. Yes. Yes. So when I write the symbol q of t, I mean a complete basis of eigenstates at time t, or I mean an eigenstate of the q operator at time t. Good. Question.
So is QI not also an eigenstate of PQ?
Well, QI is what do you mean by QI? QI will be an operator of an eigenstate of Q at time Ti, but at some later time it would not. So just to make this maybe a little bit more explicit, let's take a state where the particle is at position q at time t. And then so then the state at some later time, t prime, is going to be given by e to the I h t minus t prime, acting on that original energy eigenstate. And this state, this guy, that Hamiltonian has a p squared in it. So the wave function is going to spread out. So this new state at later time t is no longer an eigenstate of the operator q. Right. I mean, so yeah. So that's why I needed to insert a complete basis of states at that intermediate time t. Question?
So if you compute another operator,
Mm-hmm.
different from Q, for example, a
Good.
function of 3,
Yes.
and the expression will be the same with a classical quantity with the base.
Absolutely. Oh, the only difference being that you would have to do the phase space integral rather than the configuration space integral. Okay. Yeah, that's a great question. So for example, if you wanted to compute a correlation function of q's and p's, then you would have to go back up and use this formula here where we think about the q's and p's as variables, the p's as independent variables, and then you would insert some q's and p's and you would get some time-ordered product. Yeah, absolutely. Other questions? Okay, good. Have you seen that before, this computation of expectation values in path integrals? You have not. So what did you do when you studied path integrals? Not much, probably. Okay, good. Okay, so there's one more important and slightly subtle point that I want to emphasize before we wrap up our discussion of path integrals just in quantum mechanics. Okay. So far, what we've been discussing is the transition amplitude between states where the initial and final states are position eigenstates. But of course, in general, we're going to be interested in computing transition amplitudes between other sorts of states. Okay? And to understand, so to discuss other states, in principle, what you want to do is you want to write some general state, psi of t, at time t, in this basis. So you would write it as an integral of dq of q of t times the wave function of psi in the position basis. Okay. So this overlap here being a fancy name for the wave function psi of q at time t. And so using this, you could just go ahead. So for example, if you want to compute the transition amplitude between one arbitrary state given by some wave function and some other arbitrary state given by some wave function, what you would need to do is you would need to compute the path integral I've given you up above, and then you would need to integrate over the initial and final boundary conditions in order to set the state equal to some arbitrary initial state, psi initial, and some final state, psi final. Okay. For example, one state that we might be very interested in understanding is the vacuum state. So, for example, if we want to compute expectation values in the vacuum, then what you would need to do, or in quantum mechanics we usually don't call it the vacuum, we call it the ground state. Okay. Then what you would need to do, so the vacuum time-ordered expectation value of some product of these observables, q of t, well, you would just integrate overall. Well, so first what you need to do is insert two factors. So let's call, I don't know, your initial, so I guess I call them T1. Why don't I not use, because I was using T1 and Tn to be my initial and final endpoints. So let's call them T2 up to Tn minus 1 here to keep more consistent with the notation that I was using. I would need to integrate overall initial and final positions, Q1 and Qn, times the ground state wave function at times T1 and Tn. And I have this complex conjugation here because, sorry, I guess that would be a Tn, and this would be a T1. There would be that complex conjugation here because that's the overlap between the ket psi, the bra psi, and the bra Qn-Tn. And then you would need to do the path integral e to the is over h bar with the insertions at times T2 up to Tn minus 1. So all I'm doing here is I'm using the fact that I can rewrite my vacuum state. So this is my ground state wave function here. This is the ground state wave function. And then I'm rewriting the vacuum expectation value on the left-hand side as a sum of ground state wave functions times the transition amplitude, or this expectation value, in the position space eigenbasis that we were using above. Is this more or less clear? Any questions on this? So just to make this a little more explicit, this path integral is one where q at time t1 is equal to t1 and q at time tn is equal to tn. So in particular, what we see is that if you want to consider expectation values of these observables in a state that is not the vacuum, all you need to do is change the boundary conditions in your path integral. Okay. So instead of just saying q at t1 is equal to t1 and q at tn is equal to tn, what you need to do is you need to do the computation for all values of q1 and all values of qn. Then you need to integrate over those initial and final values with some appropriate factors of the wave function. Okay. Are there any questions on that? I'm getting a couple of blank looks. Okay. Yes? Sorry, q of t1 is q1. Oh, I'm sorry. Are those the blank looks that I was getting? Yes. Okay. Okay, sorry about that. So q at t1 is q1, q of tn is qn. And then we integrate. So, so for example, if you wanted, just a very simple example, if you wanted to compute a transition amplitude, not for a particle to be at position q1 to position qn, but instead of a transition amplitude where the particle starts in a superposition of states at q1 and q1 prime and qn, well, you would just use the superposition principle and you would write the sum of the two transition amplitudes. And that's exactly what I've written here. So that would just be the case where that wave function psi is just a sum of two delta functions. Okay. So in order to compute this explicitly, it appears, we need to know the ground state wave function. But now what I'm going to do is I'm going to introduce a kind of sneaky trick, which allows me to never actually think about the computation of these ground state wave functions. Okay, this is really kind of a sneaky trick. A lot of people complain about this trick. Okay, this is a trick with a very long history of people complaining about it. Okay. But it is a nice trick. Which allows us to forget completely about this ground state wave function, psi of q. Okay. And the trick is the following. Okay. So let's imagine that we have some state q of t. And we want to think about this as the time evolution of some state. Okay. How do I want to write this? So let's imagine that we have some state, psi, at time t, and we want to think about it as the time evolution of some state where the particle was in position q prime at some earlier time t prime. So let's imagine expanding this right-hand side in terms of energy eigenstates. Well, what would this look like? You would sum overall energy eigenstates, so let's just label them by some label that I'll call n, of e to the I en t minus t prime times the overlap between one of these energy eigenstates and the state q prime at time t prime. I guess I should have a t prime there. Okay, so I haven't actually done anything yet. I'm just imagining expanding in a set of energy eigenstates. Okay. So let's now imagine doing the following. So imagine that instead of the Hamiltonian h, I replace the operator h by a different operator, a non-Hermitian operator, an operator where I add a small imaginary part to h. Okay. Then what happens if you act with this new operator on our initial state? Well, that goes to e to the I 1 minus I epsilon h times t minus t prime, acting on q prime t prime. Or, if you expand in terms of these energy eigenstates, you get factors of e to the I 1 minus IE times these factors e to the I en times t minus t prime. So now let's imagine that we have some quantum mechanical system where all of the ENs are positive except for the ground state, which has energy 0. We can always shift our energy so that the ground state has energy 0. Okay. Then what happens is that at very late times, as t goes to infinity, you have terms that go like e, sorry, let's say, yeah. At very early times, as t goes to minus infinity, you have terms that go like e to the minus epsilon en times t minus t prime. Okay, no, sorry, let me restate that. At late times, as t goes to plus infinity, you have terms that go like e to the minus epsilon en times t acting on this state, which will vanish exponentially quickly at late times unless en is equal to 0. Okay. So that means that at late times, this will just project onto the ground state. Okay. So it goes to 0 unless en is equal to 0. Okay. So what that means is that e to the I 1 minus I epsilon h t minus t prime acting on this state q prime will approach the ground state at late times. Okay. So it approaches the vacuum state as t goes to infinity. Times some normalization factor, which was just the overlap of the original state q prime with the vacuum state. Okay. So what this means is that starting with any state as long as it has non-trivial overlap with the vacuum, evolving with not the Hamiltonian, but the non-Hermitian operator 1 minus I epsilon times the Hamiltonian, picks out the ground state at late times. Or, to say this a little more precisely, if you start with any ket and evolve with e to the minus I epsilon h by acting on it from the left, then you'll approach the ground state at late times. And likewise, acting with 1 minus I epsilon h on any bra vector will pick out the ground state at very early times. Simply because, for the same reasons. So what that means is that we can actually do something rather sneaky. Okay. So let's say we want to compute this expectation value in the vacuum state. So let's imagine doing this by a path integral. And to make things a little clearer, let's think about the phase space path integral. So with the integral of p q dot minus h. And in order to compute this in the vacuum state, rather than inserting explicitly the ground state wave functions, we could just adjust the Hamiltonian so that instead of the Hamiltonian being the previous Hamiltonian, the Hermitian Hamiltonian h, we insert a factor of 1 minus I epsilon there. And this will automatically pick out the ground state for us. And in fact, there's a slightly different way of interpreting this, a somewhat more geometrical and a bit more confusing way of interpreting this, okay? Which is to think about this as an alternate way of computing path integrals, where instead of time being real, time is now complex. In particular, if you just make the change of variables, so you define some new time coordinate, which is 1 minus I epsilon t, then you can see that dt tilde is 1 minus I epsilon dt, so that this term here is just h times dt tilde. And dq by dt times dt is just dq by dt tilde times dt tilde. Okay. So that means that the path integral that picks out the ground state is the usual path integral in quantum mechanics, the only difference being that we now think about the integrand of this path integral is not the expectation value of an action evaluated as a real-time integral, but rather as an integral over a contour in the complex time plane. Okay. So time is now complex. And instead of integrating along the real-time contour, we integrate along some slightly rotated contour that looks like that. And of course, this also works in configuration space, so we could integrate dq of the exponential of I over h bar times the action. But now the action is the integral of the Lagrangian along this contour through the complex time plane. And here, dot here means d by dt tilde, not d by dt. Okay. So this process where we rotate the contour of integration is known as Wick rotation. Okay. You know, it's a kind of notoriously tricky procedure. It takes some getting used to. From a practical point of view, often the way that we think about Wick rotation is that it means that you just imagine computing everything in a Euclidean theory. That is to say, a theory where you just take t to it. Okay. We call that a Euclidean theory because if you take t to it, then the line element of special relativity, so the line element of special relativity, you know, t squared minus x squared. If you take t to it, that just goes to minus t squared plus x squared, which is just minus the line element of Euclidean geometry. Okay. So from a practical point of view, what this means is that when we compute expectation values in the ground state in quantum field theory, what you can do is you can just rotate the contour that you're integrating in from a real-time contour to a complex time contour. Okay. So in fact, typically what people do is they don't just take t tilde to be this contour that's rotated, you know, by some small amount epsilon here, but they'll actually take the contour to be this contour here. So this is usually called the Euclidean time contour. Okay. So the Euclidean time contour. So don't worry. I mean, this is a subtlety that, from a practical point of view, is not going to make too much of a difference. But it's something that I wanted to bring up because, you know, there are cases where this is important. And we will, from a practical point of view, be doing a lot of our computations in Euclidean time, precisely because it picks out the vacuum state in this way. Okay. Yes, question?
So when you just introduced complex time above, we replaced h with h of 1 minus
Yes.
I epsilon.
Mm-hmm.
And it seemed there we required epsilon to be small.
Well, we didn't. If you think about it, I certainly, if epsilon was not, you know, just because I call something epsilon doesn't mean that it
Yeah,
has to be
it's a
small,
different name,
right? Epsilon is a, it's a perfectly nice Greek letter. I don't know why everyone thinks it has to be small all the time. But no, I mean, certainly the important point here was that epsilon had to be positive. Okay. So if epsilon was negative, then okay, things would get, a little, you would be picking out infinite energy states instead of zero energy states. And so we wouldn't quite know what to do here. So the important point is that epsilon is positive, which roughly means that we need to rotate, which roughly means that if you think about this complex time plane here and you start with the real-time contour, you need to rotate the contour in this direction rather than in that direction. Okay. Because, I mean, it's actually very similar to the sort of contour manipulations that we did when we talked about these propagators, the Feynman propagator and so forth. There's one contour rotation that makes sense and that allows you to, perform those integrals, and other contour rotations that don't. Okay. And so really, when I did this change of variables here, when I introduced the t tilde variable up here, there was no place where I assumed that epsilon was small. Okay. So you could either think about these integrals as being done where epsilon is small, and you add it as just a little tiny factor that projects you onto the vacuum state. But from a more practical point of view, it's useful to think about, epsilon being large, actually infinite would be the case where it takes you onto the imaginary time contour, or the Euclidean time contour. And that's the one where everything would be nice and sort of simple.
And then if you take epsilon to be infinite, then you don't really need to worry about taking t to be infinite, then, because
That's right. That's right. Good. Questions? Yes.
Are you assuming that the wave vacuum is the energy of the vacuum is zero?
Yes. So so one can always shift the Hamiltonian to make so we only ever observe differences in energies. So one can always just shift the Hamiltonian to have the ground state being zero energy. Okay. If the ground state does not have zero energy, there would be some extra factors that would float around here that I would probably just reabsorb into my definition of the path integral. Okay.
So you can have any other state also.
Yes. Okay. But no, I see what you're saying. So let's imagine that you shifted it so that the ground state had energy -1 and the first excited state had energy 0. Okay. Then what would happen is you would still not pick out the first excited state because all of the because where's the argument? Yeah. Because all of the states, with energy bigger than 0 would still be suppressed, but the ground state would be exponentially enhanced. And so you would have to pull out a factor of e to the minus epsilon t times whatever the negative energy, the absolute value of the energy of the ground state is. Okay. I would probably just reabsorb that into my definition of the path integral, and which is, I mean, essentially shifting the ground state energy is just adding a constant to the action. Okay. Adding a constant to the action is just multiplying this dq here by an overall factor. Okay. So, that is just, I could call that part of my definition of dq if you'd like.
Okay, and if you look up, you multiply I by I minus I epsilon.
Yeah. So, unless I got the signs wrong, in which case epsilon has to be negative. What's that? Oh, I'm sorry, there's a minus, and there's a minus, and there's a minus. Sorry about that. Okay, and so there's a plus. So did I get okay, did I get a minus sign wrong? It's still a minus. Okay, did my minus, it's certainly possible. Minus. Okay, it's always possible that I made a minus sign mistake. In which, yeah, okay. Can I, if I put a plus or minus there, will you be happy? Okay, it's one of those. Let's see. Should we get it right? Okay, there's an e to the minus iht here. Okay.
You have to be plus and then
Oh, no, I'm
the
sorry.
coefficients, you get a minus sign because
No, I'm sorry. No, it's a plus. What am I doing? There's no minus sign there. Okay, no minus sign. But there is there's a plus sign here. So so there's a plus sign here. Oh, I'm sorry. So, it picks out, I'm sorry. Okay, no, the point is the following. Remember the initial, the ket vector, so it's at early times. The ket vector is the initial state. Okay. So the point is that as t goes to minus infinity, this picks out the ground state. Okay. And the bra state is at late times. Okay, I'm sorry about that. Yeah. So everything's correct. I just made a mistake when I can't apparently multiply signs together. Yes, so the initial state is the ket vector, okay? And that's the one, and so you evolve with e to the minus I epsilon, and then as t goes to minus infinity, you get only the ground state. And as t goes to plus infinity on the bra, which is the final state, you get a ground state as well. If we had decided that we were going to compute not the bra at late time and the ket at earlier times, but the bra at early time and the ket at late time, I would have needed the operator e to the 1 plus I epsilon h, not 1 minus I epsilon h. Good. Yeah. Sorry about that. Okay, good. Any other questions? Okay, so I understand that this is all rather abstract. This is a bit abstract at this point, but don't worry. Next class we'll be getting much more down to earth and using these path integrals to actually compute some Feynman diagrams. Okay, see you next week.